Okay, what we're going to do for the next little while within this module, we're going to talk about the nutrients that we take in large amounts. And so a couple of the terms you hear about is you hear about macronutrients and micronutrients. The macronutrients that we're taking in grams, okay, all the time. When you read nutritional labels and you read grams of carbohydrate and grams of saturated fat and grams of unsaturated fat and grams of protein, okay, versus when you look at your micronutrients, okay, your vitamin C and your vitamin B this and your vitamin D and your all of those, we're taking in very small amounts. So our macronutrients being these big ones and our micronutrients being these small ones. And so we want to look at these macronutrients. Specifically, we want to look at our carbohydrates, we want to look at our fats, and then we also want to look at our proteins. Well, we're going to begin with our discussion of carbohydrates. So the question is, well, where does that term carbohydrate come from? Well, if we break it down and we kind of split it here after carbo and hydrate, carbo, carbon, and hydrate, water. And so if you look at your carbohydrates, okay, and our carbohydrates have big, long-ish, okay, they can be short, they can be longer, okay, not huge like some of our fats are, okay, and some of our big, long, complex proteins are, okay, but notice it's a chain of carbon. In this case, there's 6 carbons long. And notice, okay, so we got the first part of the word. Now we got to hit the hydrate part. Well, notice with each carbon overall, okay, we have a carbon with an H2O attached to it. A carbon with an H2O attached to it. A carbon with an H2. So notice that if we number the carbons and then we look, we say, oh, wait a minute. For every carbon, there is a corresponding water molecule. So that's where the term comes from. So it's watered carbon. And why do they become important to us? Okay, and it is its relationship to how many carbons and how many water. So if you look at the general molecular formula for a carbohydrate, it has the formula where X is the number of carbons, that there's 2 times that number of hydrogens and that number of oxygens. Okay, so if this was 4, let's say 5 carbons long, that means there'd be 5 carbons, there would be 10 hydrogens, and there would be 5 oxygens, okay, to be a carbohydrate. And it's that principle that actually makes it so it's soluble in water. Now, very often, these carbohydrates like to form rings. Now, the relationship we want to make here is, well, why do carbohydrates dissolve in water? Now, back when we talked in the last module, we talked about, well, why do things like to dissolve in water? And we used the statement that like dissolves like. That when we looked at the water molecule and we looked at it, let's draw it, we looked at it and said, all right, here's the water molecule. Here we had an oxygen, here we have a hydrogen, here we have a hydrogen, okay? And we said that this side of the molecule was a little bit negative, using the delta sign. This side is a little bit positive. And why was that the case? Well, the situation was this is a covalent bond. And in that covalent bond, there's 2 electrons there. And we had, in this covalent bond, we had one of the atoms that was more electronegative than the other. So oxygen being to the right and the top of the periodic table is very electronegative. So it has a very strong pull on those electrons. And so it made this side a little bit negative and this side a little bit positive. Well, now, if you'll notice on your carbohydrates, we'll notice for every place there's a carbon, oh, look at, there's the OH. And so we have the same scenario where when I have an OH, I have a little bit negative and a little bit positive. So if I have a carbohydrate that has a little bit negative and a little bit positive, and I have a water molecule that's a little bit negative and a little bit positive, well, they're going to like each other. And therefore, like dissolves like, therefore carbohydrates being watered carbon, well, of course, they're going to be able to dissolve in water. So that's the relationship. All right, so in this case, we won't get into a great deal of detail of why we number the carbons the way they do, but notice where this carbon has the double bond attached to it, that we list that as carbon number 1, and then we just number them in the chain. Now frequently these carbohydrates like to form rings, and so we find that carbon, and it's 1, 2, 3, 4, 5, 6. So in this carbohydrate there are 6 carbons. Well, that means if I asked you to, could you write the molecular formula? Yes. It would be C6H12O6. Why? because for each carbon, I got to have a water, okay, that's attached to it. And what we do is, notice we don't like to draw all this, and so very often we draw abbreviated structures, where in this case we said, you know what, we don't need to draw all these C's, okay, and in many cases we don't even want to draw the H's, so we only write them in abbreviated form. We say, all right, we just want to write the C's, we just want to show the ring, and we want to only list those molecules that are really significant, okay, for us. And so we try to write kind of shorthand versions as much as possible. Now, one of the things we do with these carbohydrates is we list them, we put them in groups based on the number of carbons they have. So for example, with pentoses, penta meaning 5, hex meaning 6. So our pentoses have 5 carbons, our hexoses have 6 carbons. Now, don't confuse shape with carbon number. So a pentose has 5 carbons. Doesn't mean it's a pentamer structure. Hexoses have 6 carbons. Doesn't mean it's a hexagon structure. Frequently they do, but they don't have to, okay? Because notice, okay, when we get into some of these other structures, there are 6 carbons, but they don't all have, okay, a hexagon shape. For example, glucose, fructose, and galactose, okay, are all C6H12O6. So they all have the same molecular formula, but they have a different structure. Okay, remember those are isomers. So an isomer is, okay, again to give that definition, same molecular formula, different structure, and that's where carbon and all the different bonds and all the different ways it can be formed, that's where that can change. So glucose, fructose, and galactose are all C6H12O6, but there's a big difference in how does this one taste versus how this one tastes versus how this one tastes. Okay, and you can actually go online, and there's what we list is a sweetness scale, where everything is basically based on the taste of sucrose, our table sugar, and then everything is more or less sweet based on that. Okay, so there are sugars that aren't sweet, okay, that we classify as sugars, okay, or carbohydrates. Well, why aren't they sweet? Well, because the way the molecular structure is. Even though glucose, C6H12O6, fructose, C6H12O6, and a totally different shape, and therefore a totally different spot on the sweetness scale. Same thing is true of galactose. So we're going to put these together into, for example, if I take a molecule of this and a molecule of this, well, what does that make? Okay, well, we like it when it's in ice cream. Or we take a molecule of this and a molecule of this, well, what do we like about that? Okay, and so we'll describe that more as we start putting them together. So when we look at single molecules of sugar, we refer to those as monosaccharides. And they can really be anywhere from 3 carbons to about 7 carbons, and then a corresponding water molecule to go with that. So glucose, which is our main blood sugar and the nutrient we use for energy. Fructose, of course, being our quote-unquote our fruit sugar. Galactose as a component of milk sugar. Okay, it's not milk sugar, it's a part of that. Okay, lactose is your milk sugar, and it actually contains, and we're going to get into that in detail upcoming, a molecule of glucose and a molecule of galactose. Deoxyribose and ribose in DNA and RNA. So if you look at those, DNA versus RNA, ribose and deoxyribose, what would be the difference? Deoxy meaning lacking that oxygen. So if you'll notice down here on this hydroxyl functional group, notice ribose has an OH, and deoxyribose is missing that O. So deoxyribose and ribose, that's the difference between DNA and RNA. Now, does it have a functional difference that's important to us? Oh, yeah. Okay, and we'll get into that in detail in the next module, more than maybe you wanted to know. Okay, but we'll get into that, okay, in modules 4 and 5, okay, as we talk about how cells work. Okay, so hopefully that helps you understand, okay, kind of how we build these carbohydrates.